Have you ever wondered what lurks beneath the surface of our planet, driving the cataclysmic events that shape our world? Earthquakes that shake continents, volcanoes that spew rivers of lava, and massive eruptions that alter climates, these are the manifestations of Earth's fury. But what fuels them? Deep within the Earth, hidden from our eyes, lie mantle plumes, colossal upwellings of hot rock that rise from the planet's core, punching through the mantle and unleashing chaos on the surface. In this exploration, we'll dive into the science of mantle plumes, uncovering how these invisible forces power some of the most dramatic geological phenomena on Earth. To understand mantle plumes, we need to peel back the layers of our planet. Earth is like a giant onion, with a solid inner core of iron and nickel, surrounded by a liquid outer core. Then the mantle, a thick layer of semi-solid rock that makes up about 84% of Earth's volume. And finally, the thin crust we live on. The mantle isn't uniform, it's a dynamic, churning sea of rock heated by radioactive decay and residual heat from Earth's formation billions of years ago. Mantle plumes originate at the boundary between the core and the mantle, around 2,900 kilometers below the surface, where temperatures soar to over 4,000 degrees Celsius. These plumes are essentially thermal anomalies, columns of hotter-than-average rock that become buoyant and ascend through the denser surrounding mantle. Imagine a pot of simmering soup. Heat from the bottom causes bubbles to rise, carrying warmth upward. Similarly, mantle plumes act as conveyor belts for heat, transporting it from the deep interior toward the surface. As they rise, the plumes can stretch up to 2,000 kilometers in height and span hundreds of kilometers in width. The rock within them isn't fully molten, it's mostly solid but plastic-like, deforming under immense pressure and heat. What makes mantle plumes so powerful? It's their ability to melt rock as they approach the surface. When a plume reaches the base of the lithosphere, the rigid outer layer comprising the crust and uppermost mantle, the drop in pressure allows partial melting to occur. This generates magma, the molten rock that fuels volcanoes. Unlike the subduction zones where tectonic plates collide and create volcanic arcs, mantle plumes create hotspots, fixed points of intense volcanic activity that seem independent of plate boundaries. One of the most famous examples is the Hawaiian Islands. Hawaii sits in the middle of the Pacific Plate, far from any plate edge, yet it's home to some of the world's most active volcanoes like Kilauea and Mauna Loa. The Hawaiian hotspot is the surface expression of a mantle plume that has been active for at least 80 million years. As the Pacific Plate drifts northwest over this stationary plume, it leaves a trail of volcanic islands and underwater seamounts, forming the Hawaiian Emperor chain that stretches over 6,000 kilometers. Each island represents a snapshot in time. The oldest, like Midway Atoll, are eroded remnants, while the youngest, like the Big Island, are still growing from ongoing eruptions. But mantle plumes aren't just island builders, they're agents of destruction. Take Yellowstone National Park in the United States. Beneath its geysers and hot springs lies a supervolcano powered by a mantle plume. Yellowstone has erupted catastrophically 3 times in the last 2.1 million years, with the most recent blast 640,000 years ago spewing enough ash to cover the entire continent in a layer several centimeters thick. Such super eruptions can trigger global cooling by blocking sunlight with atmospheric aerosols, leading to volcanic winters that disrupt ecosystems and agriculture. Mantle plumes also play a role in Earth's most devastating mass extinctions. The Siberian traps in Russia, a vast region of flood basalts, were formed by a massive plume event around 252 million years ago, coinciding with the Permian-Triassic extinction, the Great Dying, that wiped out 96% of marine species and 70% of terrestrial vertebrates. The eruptions released enormous amounts of carbon dioxide and other gases, causing rapid global warming, ocean acidification, and anoxic conditions that suffocated life. Similarly, the Deccan traps in India, linked to another plume, erupted around 66 million years ago, contributing to the climate stress that, alongside the Chicxulub asteroid impact, ended the reign of the dinosaurs. These plumes don't just cause volcanoes, they influence earthquakes too. As plumes weaken the lithosphere, they can create rifts and faults, leading to seismic activity. In Iceland, where the Mid-Atlantic Ridge, a divergent plate boundary, overlies a mantle plume, the interaction amplifies volcanism and earthquakes. The 2010 Eyjafjallajökull eruption, powered by this plume, disrupted air travel across Europe with its ash cloud, reminding us of the global reach of these hidden forces. Scientists have long debated the existence and nature of mantle plumes. The concept was first proposed by geophysicist J. Tuzo Wilson in the 1960s and expanded by W. Jason Morgan in 1971, who suggested they were fixed relative to the moving plates. However, not all hotspots fit this model perfectly. Some seem to move or wane over time. Critics argue that some volcanic features might result from other processes like edge-driven convection or slab pull in subduction zones. To resolve these debates, researchers use advanced tools like seismic tomography, which maps the mantle's interior by analyzing how earthquake waves travel through it. Slower wave speeds indicate hotter, less dense regions, signatures of plumes. Recent studies have imaged plumes beneath Hawaii and Yellowstone, showing narrow conduits extending deep into the lower mantle, sometimes tilting due to mantle flow. Satellite data from missions like GRACE and GOSI measure subtle gravity variations caused by plume-induced uplift, while geochemical analysis of hotspot lavas reveals primordial isotopes from the deep earth, supporting the plume hypothesis. Mantle plumes also drive plate tectonics on a grand scale. By injecting heat and material into the upper mantle, they contribute to the convection currents that move tectonic plates. Some theories suggest that massive plume events called superplumes have periodically resurfaced large portions of Earth, influencing continental breakup. For instance, the breakup of the supercontinent Pangaea around 200 million years ago may have been aided by plumes that weakened the lithosphere, allowing rifts to form and oceans to open. Looking to the future, understanding mantle plumes is crucial for predicting volcanic hazards. With populations growing near hotspots like the Galapagos or Reunion Island, early warning systems relying on seismic monitoring and gas emissions could save lives. Climate models incorporating plume-related CO2 releases help us grasp long-term carbon cycles relevant to today's anthropogenic warming. Moreover, mantle plumes offer insights into other worlds. On Venus, vast volcanic plains suggest plume-dominated tectonics, while Mars' Olympus Mons, the solar system's tallest volcano, likely formed over an ancient plume. Even icy moons like Europa may have cryovolcanic plumes driven by subsurface heat. In essence, mantle plumes are the unsung architects of Earth's dynamic surface, fueling its fury while recycling its interior. They remind us that our planet is alive, constantly reshaping itself through hidden forces. As we probe deeper with technology, who knows what new secrets we'll uncover. The next eruption could rewrite our understanding of Earth's inner workings. Stay curious and remember, the ground beneath your feet is far more restless than it seems.